Hi guys, good morning. So if you're there, wait for just 1 more minute, 2 minutes. If I join. Okay, fine, we'll start people. Let your friends join. Sharing screen. Right. So hope you remember, guys. We were seeing keto in automedicine, right? So it obviously involves resonance. So we saw so much about resonance also, right? So yeah. So I'll just start with a new example for keto in automedicine, right? Say, okay. Say I have. Okay. So I have this compound with me, right? So can you give me the enol? This is the keto form. This is an aldehyde form, right? Can you give the enol form of this? Just try. I'll give you a minute. Just quickly try. You know what you have to do, right? So hope you remember what and all the things you have to remember, right? The tautomerism exists because of acidic alpha hydrogens, right? So now you have to remove H plus, make a negative charge, then do the resonance, make oxygen have the negative charge, and then add the H plus again. That's it. That's my isomer. Just do this and tell me.
So what did you tell, sir? Can you just repeat?
Yeah, sure. So what I told is you have to write the enol form of this, right? So hope you remember how tautomerism exists. What is the reason the tautomerism exists? Tautomerism exists because I have acidic alpha hydrogens, right? So you can see this is the carbonyl group. I mean, carbonyl in the sense C double bond O is here. So if I write the structure properly, it will be something like this. C. 1 second. Right, this is the structure. C double bond and H. Right. So what I told you is you have to remove an alpha hydrogen because that is acidic as H plus, and then you will have a negative charge on carbon. Then what will you do? You'll do the resonance structure, right? And then you'll break the C double bond O with a single bond, and then you will have a negative charge on oxygen. Then add the H plus there. That will give you the enol form. Right. So anybody got it? Anybody have done it? No, you don't. I'm not asking whether you did correct or not. Did you do it? Is the question. Did you try? So does it mean nobody is trying?
Trying.
Okay. Okay. Fine. So let me do this for you. Maybe next one you do. Right. Okay. Say now what is the alpha position here? Now this is the carbon containing the functional. This is my functional group. right? So this is my alpha carbon atom, and if you remove this hydrogen, guys, I'm really sorry, that is not the thing which you have to do, right? So this is the functional group. This is the carbon atom which is in the alpha position, and these hydrogen atoms here are the alpha hydrogen atoms, right? So now I remove the H plus minus H plus from the alpha position, right? So what will you have is CH3, CH2, CH, and I obviously have a negative charge because you removed a H plus from this, and this stays C double bond O and a H, right? Now what you have to do, you have to go for the resonance structure now, because you can see resonance is possible. Pi bond, no pi bond, and again a pi bond, alternate pi bond is present, right? So now what will happen, this will come here, make a bond, and this C double bond O will break, right? So now what will be the next structure? It will be CH3, CH2, CH, double bond, CH, double bond, C, O minus, H, right? Now you removed H plus here, just add the H plus here. So I, instead of O minus, I can just write H, OH. That's it. So this is the enol form. So this is the keto form, and this is the keto form, and this is the enol form. Right? Did everybody get this? Get this structure? Anybody got this structure? Okay, fine, no issues. Let's try one more problem, and you should be getting the answer this time. Don't worry. All right. So now let me give you a cyclic structure.
So I have a doubt.
Yeah.
So in the last step, we added the hydrogen back. So
Yes. So you add a O minus here. Actually, there is one more step I skipped. Actually, you have a O minus here. Then I added H plus. You removed H plus. You add the H plus here. That's it. That's what I did. Okay. Right. So now let me give you a cyclic structure. Okay. Say the double bond O is here. Right. Go for it. Now, guys. Now this is the carbon having the functional group. Now you have two alpha positions, isn't it? Now this can be an alpha position. This can also be an alpha position. There is no restriction. You can take hydrogen from any of that and do it. Okay. Anybody has done it?
about to finish. So just a second.
Okay. Sure.
Done, sir.
Okay. So let me see. Now you check it, right? So there are two hydrogens here. One. And another hydrogen, obviously. Right, I know in a ring, each of the carbon atom will have two hydrogens, right? So anyways, so let me remove the H plus, minus H plus. Now you will see that there is a double bond O and there is a negative charge. Obviously, one more hydrogen is also there. If at all you want, you mention it, or doesn't matter, right? So there is a negative charge. Now this will come here, and obviously this bond will break, right? So what will be the next structure? The next structure will be an O minus, a double bond here. Then you add the H plus. So if I add the H plus, O minus will become OH and the double bond stays. Yes, did you get this?
Yes, sir.
Wonderful, wonderful. Anybody else got this?
So if we took the left one, the double bond will come to the
Doesn't
left.
matter. Like it's symmetrical. No, you would have got the double bond here in that case. That's it. Doesn't matter. Both are correct. Anybody else got this? Or guys, are you even trying? That's the question. Hello. Abhishek, Divya, Shruti, Venisha. Are you guys trying? Did you get the answer? Did you get the structure out?
So I didn't get it, sir.
Okay, fine, cool. We'll do one more. Oh, wait, there's some more in the chat. Okay, Venisha is also trying. Good, Venisha. Fine. So one more structure I'll give you. This time you must get it, guys. It's pretty simple. You can see the exactly same thing I'm doing in all the structures, right? Okay. Fine, wait. So say, okay, this is a 6-member ring, and say I have a double bond O, and I have a double bond here and a double bond here, right? So this is what I have, right? Now, guys, right, this structure, okay. So how many alpha positions I have in this molecule, guys? Tell me. How many alpha positions I have? How many alpha positions? Quick.
Sir, is it 2?
2, right? So obviously this is the carbon atom having the functional group. So obviously the next carbon atom, the carbon containing the functional group is alpha, again alpha. But guys, what you have to understand is in these kind of situations, right? So last time you were free to take any of the hydrogen atoms, isn't it? You can either, so you can see, you can either take from this side or you would have taken from that side. It's fine, right? But what you see here is this alpha position, in this case, the carbon atom is sp3 hybridized. Again, hope you remember, right? So this carbon atom is sp3 hybridized, and this carbon atom, what I have, is sp2 hybridized. Okay, right? Obviously, no. Whenever you have a double bond, see, remember like this: only single bonds sp3 hybridized, double bond sp2 hybridized, triple bond sp hybridized. Remember this, or you know how to calculate the hybridization, right? Okay. Now, what you have to understand, guys, you cannot remove alpha hydrogen from this position. Okay, that means there is one hydrogen atom here also. There is no doubt, right? If I may just remove this alpha, and then if I just draw a hydrogen atom, this hydrogen atom exists, and here I have 2 hydrogen atoms. Right, there are 2 hydrogen atoms here. Right, now what you have to understand is this hydrogen cannot be removed. That's what you need to understand. Why, if you ask me? Now, whenever you have, I told you, whenever S character increases, whenever the amount of S character increases, the electronegativity of the particular atom increases, right? And whenever electronegativity increases, the CH bond becomes stronger. So you will not be able to remove this hydrogen. That's what I'm telling. How do you propose? What do you mean by amount of S character? Say in sp3 hybridization, the amount of S character is 25%. Can I say that? Isn't it? You have total 4 orbitals. Out of that, one of them is S. So 1 by 4 is 5. And say if it is sp2 hybridized, right? If it's sp2 hybridized, can I say it's 33.33%? Right? Because you have total 3 orbitals and one of them is S, right? And obviously in case of sp hybridization, you see that it is going to be 50% S character. Again, you see there are 2 orbitals, one of them is S, so 50%, right? So when I have an sp2 hybrid or sp3 hybridized carbon, it is the least electronegative. sp2 is more electronegative, and sp hybridized carbon is very, very electronegative, as much as electronegative as oxygen, right? That's what you need to understand. So what I'm trying to tell you is that if the electronegativity of the carbon increases, the CH bond strength also increases. So you cannot remove the H plus from there. right? Now we have to remove only from the sp3 hybridized carbon. Okay, now you go for it and tell me the answer. Same thing. I want everybody to try. I want everybody to get the structure out. Do not sit idle, please. Exact same thing what we did last time. Okay, I'll give you 30 more seconds. Okay, hope you're done. How many have you finished? Nobody finished.
No, sir.
It's not a big deal, right? This same thing, remove the H plus, negative charge, resonance, oxygen negative charge, add the H plus. Same thing. Yes, it should be done this time. It should not be taking so much time. Is it done? Okay, so
Done,
let me
sir.
draw the let me draw the structure. You check out. So again, I'm going to remove any one of these hydrogens, right? So okay, there is a double bond O, there is a double bond here, and there is a negative charge. Then the next step would be to this and to break this, and next O minus a double bond, and a double bond. I mean, properly, and a double bond. Okay. Right now, what is the next step? Add the H plus. Right? When you add the H plus to the oxygen over there, make some space. Okay, so you have OH, double bond, oh wait, oh sorry, no, this is not there. So there's a double bond here, double bond here, a double bond here. Okay, and a double bond here. That's it. So this structure, guys, is a very famous chemical compound. Anybody knows what is this compound? Anybody knows what is the name of this compound?
It's phenol, sir.
Exactly. This is phenol, a very, very important, say, industry-wise, or say your chemical synthesis-wise. Every way, this is very important. And guys, your famous phenyl, the famous how we call it, we use for toilet cleaning. It is actually this. Right? It's actually phenol, but phenol became phenyl. Right? Sad, isn't it? So this is what we use generally for toilet cleaning. This is pretty acidic. Okay, you will see about it when I go for a little in this chapter itself. Okay, so this is what is phenol, right? Okay, so fine. So hope you understood. Now any keto form given to you, right? If you have alpha hydrogens, you can directly write the E0 structure. Easy. right? So yeah, that is about tautomerism, people. So we have completed structural isomerism. One part of isomerism is over, right? So any questions, guys? Any questions you want to ask regarding any structural isomerism? Okay, fine. So I suppose everybody is okay, right? So now we'll move on, people. We'll move on to the next type of isomerism. So I told you isomerism can be broadly classified into structural and stereoisomerism, if you can remember, right? So again, under stereoisomerism, you have again two more types, right? I told you one is called as geometrical isomerism. The other one is called as optical isomerism. And this I told you we'll see in 12th class next year, right? And this we'll see now. Right? What do you mean by a geometrical isomerism? Right? Now, going back to the definition of what isomerism is, can you tell me the proper definition of isomerism? Not structural, not nothing, just isomerism. Give me the proper definition. How do you define isomerism?
So two or more compounds having same molecular formula but different structures or different orientations of atoms.
Absolutely true, right? So if you're gonna just stop with say molecular formula but different structure, then you're talking only about structural isomerism, right? But if you include the other statement, that is different orientations of atoms in 3D space, then only you can account for stereoisomerism. Right? Okay. So what we understand from the definition is that obviously, you know, carbon atom can be tetrahedral, right? Because it's, if at all there are no double bonds or triple bonds, I know carbon atom can be tetrahedral, right? So obviously tetrahedral is 3D structure. Hope you know how it looks, right? One bond coming towards you, one bond going away from you, right? Hope you remember how do you represent it. Say for example, if I represent CH4, this is how I represent CH4. One wedge I put, right? And one dash structure I put. Now this bond tells you that whenever you put a dash structure, guys, that means the bond is going inside the plane, going up away from you, right? And whenever you put a wedge like this, that means the bond is coming towards you. It is coming out of the computer screen or say the mobile phone screen, whatever you are seeing, right? So anyways, you can see they're all 3D structures, right? So fine. So anyways, optical isomerism is actually more related to the sp3 hybridized carbon, but geometrical isomerism is a little different. We'll see what is that. Okay, fine. Okay, so guys, for geometrical isomerism to exist, right, or let me put it that, okay, fine. For geometrical isomerism to exist, you require a C double bond C. Okay, for geometrical isomerism, right, you require a C double bond C. Okay, right. So what am I going to do with C double bond C's? Right now, I hope you understand. If I have a C double bond C, right, for each of these carbon atom, there will be two more bonds present, isn't it? If at all I have a C double bond C, for each of these carbon atom, there will be two other bonds. 1, 2, 1, 2. Right. Okay. So it's all going to be the position of these four groups. If whatever I'm going to place here, right, they will have different origins. Say for example, say I can put a A here, right? Say so I'm just putting random example A, B, C, D if I have, right? So now see, A and B are on the same side. Same way C and D are on the same side, right? But the same structure, I'll be able to write one more this thing for the same molecule. I'll be able to write one more structure. Say I have a C double bond C, right? Say again, two more bonds are there, right? Say instead of putting, now you put A and B on the same side. Now let me put say A and C on the same side, right? A and C on the same side. Say now I have, or I cannot do like this. See, I'm really sorry. You can put A and D on the same side. Right now I can put C and B on the same side. Right, last time C and D are on the same side. In this case, B and C are on the same side. Last time A and B are on the same side. This time A and D are on the same side. So I hope you understand. This is exactly what is what. You can see that only the orientations are different. right? Only the orientations of atoms in the 3D space are actually going to be different. This is what is called as geometrical isomerism. Okay, now you can ask me, sir, why are you not doing it in a single bond? Right? If I have a C single bond C, guys, right? When I have a C single bond C, again you can see there'll be 3 more bonds, right? There'll be 3 more bonds, right? Okay, so obviously you can ask me, sir, again I can have the same thing as you said. Yes, it is possible. I am not denying, right? But what happens is, guys, what is the difference between a C double bond C and a C single bond C is that a single bond can undergo rotation. Right, a single bond can undergo rotation. So if you ask me what kind of rotation if it's going to undergo, it's pretty simple, right? You can look at it. In this bond, I have 2 electrons shared, right? Say this carbon atom will undergo, say, clockwise rotation, and this carbon atom will undergo an anti-clockwise rotation, right? Say, if I think I have to switch on my video and show you. 1 second. Let me flip my laptop. Okay, I hope you're able to see me, right? So guys, what I'm trying to tell you is, say if this is the single bond, right? If this is a single bond, the bond can rotate. Say if this goes clockwise, this will go, okay, say I hope like this. Okay, say something like this I have, right? Say now this, right, this one, say if it undergoes this rotation, this will undergo, say, this rotation, or say this rotation. So it's like this. It's gonna go like this. It's gonna just twist. You can see why it's happening, right? It's happening because I have the single bond, right? And you in the single bond, you see there is 2 electrons shared, one in the clockwise spin, another in the anti-clockwise spin. So accordingly, the bond will rotate, right? Okay, fine. Why is this not possible? Okay, let me stop my video, guys. Right? Okay, I think it's after a very long time you are seeing me, right? Okay, fine. Yeah, so as I told you, this single bond can rotate, right? So obviously if it rotates, again I can have also, wait, I have again flip my screen. 1 second, guys. Right? So if the single bond rotates, right, if the single bond rotates, so obviously you can see that I can have different orientations between this and this, no doubt about it. But that I'm not going to call it as geometrical isomerism. Right now, that has a different name. It is called configuration or conformational isomerism. But next we'll see that. We'll not discuss it now, right? But when I go for the double bond, people, right? When I go for the double bond, this double bond cannot rotate, right? This double bond cannot rotate. Now I hope you understand why. Again, if you try to rotate the bond will actually break, is it not? Right? Hope you understand. How, you know how pi bonds are formed, isn't it? Pi bonds, basically, I would have had a oops. Right, I would have had a lateral overlap of p orbitals like this. Right. So basically, when you have a double bond, this single bond rotation is not possible, because if you break, right? I mean, if you rotate, you will see this, whatever the kind of rotation I'm talking about the last time, you will eventually break the pi bond. Okay, so that is why in double bond or triple bond, the rotations are not possible. Okay, so whatever the orientations, whichever place I'm writing this ABCD, all these I am doing, right? All these I am just putting it in various positions and checking whether they are different or same, right? But in this case, you will get different orientation. Sorry, in this case, in the single bond case, you will get different orientations of atoms in 3D space, but I am not doing anything. The molecule is rotating, and because of that, the orientations are different. Okay, but here in case of a double bond, it like all the orientations are different because I am doing it. I'm just checking. I'm just writing it on paper, right? But in this case, in case of a single bond, you will have different orientations between this carbon and this carbon, but not because of me. It happens because of itself, because of the bond rotation. Okay, now this is not called as geometrical isomerism, it's called conformational isomerism. That we'll see in a little while after we finish geometrical isomerism. Okay, this, I would say, this is not even a stereoisomer, right? See, please understand stereoisomerism, right? Stereoisomerism, both optical as well as both optical as well as geometrical, we are doing it on paper, just like all the other isomerism except tautomerism, right? But configurational or conformational isomerism, that happens because of bond rotations. That again, that is why it is not under stereoisomerism. It is different. Okay, so fine. So let us concentrate on geometrical isomerism now, right? Okay, so as I told you, I require one C double bond C for sure for geometrical isomerism to exist. Okay, and please understand there is one more name for geometrical isomerism. It is also called as diastereomerism. D-I-A. Diastereomerism. Okay, and this is actually an S, guys. I'm sorry, my handwriting is so bad. I'll write it again. Okay, so it's called diastereomerism. It's just a different name, right? So geometrical isomerism, or it's also called as, or geometrical isomers, or they are called as diastereomers. Okay, right? So you will be using this term more and more in the case of optical isomerism, but still, this holds good. Geometrical isomerism or diastereomerism is going to be same. Okay, fine. So let us actually continue. Now, we understood that one of the definite conditions we need for geometrical isomerism is that I should have a C double bond C, right? Okay. Now it's not the only condition, people. Right. So first condition is obviously I need to have a C double bond C, right? Now second condition is you are going to look at the other two bonds which are present in each of these carbon. Right. So when you look at that, you have two more bonds in each of these cases. Right. Okay. Now the thing is, guys, each of these carbon atom, right? Each of these carbon atom should have two different groups in their two bonds present. That means, say, if I have an A, right? If I have an A, this should be something else, say B or C or whatever it is. Right, and same way, if this carbon, again for these carbon atoms, these two bonds must be different in the sense that, say, if this is A, this can be B. Okay, or you can even have A, B, C, D completely different. These two, you can see there is a pair of groups here, right? Or you can even have four different groups. That is also fine for me. The next condition, I mean, the next type can be, say, A, B, C, and D. This is also okay, or this is also okay. Okay, but you should have different, definitely these two should be different for each of the carbon, right? The two bonds which you have should have two different groups. Same way for this carbon also, you should have two different groups. You cannot, you say which and all cannot be a possibility. I'll tell you. Say this cannot be a possibility. If this cannot give geometrical isomerism, like something like this. Say I have A and A, say B and C. So what you see here, these two are okay. These two are different, but these two are same. So this cannot give geometrical isomerism. For both the carbon atoms, both these bonds, other two bonds, must be two different groups. Even if one of them is same, then you should say that geometrical isomerism is not possible. Okay, fine. Now let me concentrate. Now, guys, if you see here for this structure, right, you see that A and A are on the same side. Same way, B and B are on the same side, right? So whenever you see two groups are on the same side, right, now those kind of structures are what are called as the cis geometrical isomers. Okay, they are what are called as CIS, cis geometrical isomers. Right, now for the same thing, I can have different orientation by placing the atoms in a different way. What different way? Say I can have the C double bond. Now say two other bonds, right? Now you have put A and A on the same side. Now say I put A and A on the opposite sides. Say you have A here and I put the A here. Okay, A here and A here. Say you put the B here and another B here. So now the A and A are opposite, B and B are opposite. Now this kind of structure, whatever you get, is what is called as trans isomers. Right? The geometrical isomers are only two types. I mean, two forms of geometrical isomers. One is the cis form, where you see the groups are on the same side, and when you get the trans form, the groups are on the opposite side. Okay, fine. So let us take some good examples. Right. So, guys, if let me give you a structure and you tell me whether geometrical isomerism is first possible or not. Right? See. Okay. Now tell me, guys, if for this geometrical isomerism is possible. Okay. Now let me tell you like this. Whenever you see a complicated structure like this, okay, it's not a complicated structure, but this is a structure. So whenever you see any structure, now take out your whichever carbon atom is having a single double bonds. So let me put it like this. So you write a C double bond C first, right? I'm just representing it like this, right? Fine. So now you see for this carbon, there would have been a hydrogen also. Correct, right? Say now for this carbon, again, there would have been a hydrogen. Or if you, whenever you find problems, you write the CH3, CH2, CH, double bond, CH, CH3, something like that. Right. Okay. So now what do you see? Now you have a C double bond. See? Now tell me, if you look at the structure and just fill these 4 bonds for this, now what do you see? Will they show geometrical isomerism or not?
They will, sir.
They will show. Yes. So now you see for this carbon, there is a hydrogen atom. And what is the other group? The other group is this. I mean, this is the other group. That is basically a CH2, CH3 group. That is an ethyl group. I write it as ethyl. Hope you understand why is it ethyl. Right. This carbon atom is attached to 2 other carbon atoms, CH2, CH3. Same way. For this, there is a hydrogen atom here. Again, you can put either a hydrogen atom in the cis position or in the trans position. That will become the isomer. And you see, again, this is the only functional. In this case, it's going to be a methyl group, CH3 group. Correct. So definitely you see there are 2 different groups on the same and on the carbon atoms. So this can show geometrical isomerism. Now again, this is the cis form because you see H and H on the same side. Now I can even write the transform of this C double bond C, H, and a H. Right. And obviously you have an ethyl group and a methyl group. That's it. Right. Now this is my trans isomer. This is my cis isomer. This is my oh god.
So I have a doubt.
Yeah.
So if any compound has geometrical isomers, sir, that means it will also have one cis and one trans always. Any geometrical.
Yes. Geometrical isomerism means cis and trans. That's it. Yeah, if it allows cis and trans. But I can have more than if I really want to complicate it. Okay, let me go into that. It's not like, say, if I have a C double bond C and the conditions are satisfied, that is 2 different groups are there. When you have only one double bond, no problem. Right, but I can have multiple bonds. So I can have multiple double bonds, and then it becomes a little complicated. But I don't think that much they'll ask you. Okay, maybe for higher competitive exams, maybe that level is okay. But for your level, just understand that they'll give you only one single bond, sorry, one double bond, and then they will ask you to write the structures of cis and trans. That's it. Okay, fine. Next question. Right, say if I give you okay, wait. Okay, guys, then tell me whether this thing is possible or not. Geometrical isomerism is possible or not for this. Yes, no. Wait, let me show you the structure. Yeah, okay, this is the structure. Right, tell me, is geometrical isomerism possible for this compound?
No, sir.
No, not possible. They can just see here. You can have a C double bond C here, right? And there are two same groups on each of these carbon atoms. So this definitely is not going to show geometrical isomerism. Okay, right. Now, guys, the next question is: if I have cis and trans, any structure, any compound capable of giving geometrical isomerism having cis and trans, the question is which is more stable? Is the question. Okay, which is more stable is the question, right? So the answer to this question would be trans, right? Why? Because now if it is trans, we can see if the ethyl group and the methyl group in the last time are on the same side, they will have interactions. That means they will have repulsions coming, right? But if the ethyl group and methyl, not only in this case, for any case, trans will be actually more stable because the atoms will be, I mean, the groups will be little far away from each other, right? And I can say that there will be lesser repulsions in case of trans. Okay, so again, someone asks you which is more stable and what is the reason, you tell them the trans is more stable because of lesser repulsion. That's it. Okay, now actually this geometrical isomerism is also possible in case of cyclic structures. Okay, but I don't guys, did you see cyclic structures having geometrical isomerism in your school? Did you see that? I don't know whether it's there in a syllabus, but again, I can just give you a brief introduction. Say now in cyclic structures, say I take a 5-membered ring or whatever the membered ring I have, right? So please understand, guys, there are obviously in each of the carbon atom, there are 2 bonds. I know that, right? Now, each of these bonds are not going to be in the same plane, right? So you will see that one bond, right? One bond will be like this, the other bond will be like this. Say if I have 2 hydrogens, one hydrogen will be pointing towards you, another hydrogen will be pointing away from you. Same way, this will have a double bond, I mean, say bond pointing away and a bond pointing towards you and a bond pointing away. So each of the carbon atoms will have 2 bonds, and each of these bond, in all these cases, one bond pointing towards you, the other bond pointing away from, right? Okay, so here also I can have system trans, right? Say for example, if I write this name cis 1 comma 2 dimethyl cyclohexane. Okay, if I write like this, cis 1 comma 2 dimethyl cyclohexane. Now I know if it is cis, that means the group should be on the same side. As simple as that. Trans means opposite side, right? So let me draw the cyclohexane structure first. Okay, so this is my cyclohexane structure. Now in the first position and second position, I have a methyl group, right? So normally, how do we do it? Summa, we put a line and another line. That's it. This is what is 1 comma, just 1 comma 2 dimethyl cyclohexane, right? But what they have mentioned here is cis, so I cannot just draw it like this. I have to mention the orientation, or say whether it's pointing towards you or away from you, whatever it is, I have to mention it. Okay, so how do I go about it? Now, if for example, if you have 2 choices of putting the first methyl group, either pointing away or pointing towards you, there is no restriction, right? So let me put it pointing towards you. Oops, sorry. Okay, so let me put the methyl group, right, say pointing towards us. Okay, now if it is cis, guys, see, you can see you have put the first methyl group pointing towards you. If it is cis, you have to put the next methyl group also to be in the away, I mean pointing towards your position. That is, in this position only, right? In this position only, you should put the methyl group. Okay, fine. Or if you put this carbon atom having pointing away, this carbon atom should also have the methyl group be pointing away. That is what is cis, same side, either both pointing away or both pointing towards you. Right now, if it was trans, obviously you would have guessed what would have happened. For example, the same compound, if I write the trans molecule, right? Say now if I put this one pointing away from me, or if I point it towards you, the next one should be opposite. Now in this case, you have put it pointing away from me, say then put the next one pointing towards you. Right? Now this is what is trans, and that is cis. Same thing, same side, opposite side. Same side cis, opposite side trans. Okay, but I don't think you have this in your syllabus, but again, it's pretty simple. You don't have to worry. Like, it's not a much of a big complicated task to understand this. Right? Okay. Any questions, people? Everybody understood? Yes, everybody understood
Could you
geometrical
explain
isomerism?
again?
Yeah, sure. So what I'm telling, which you want to explain? The cyclic structure?
It's only cyclic.
Only cyclic. Okay, cool. So you can see, if I have any cyclic structure, right? If I have any cyclic structure, each of these carbon atoms will have two bonds. I know that, right? Now, how are these bonds orientated, or say how these bonds look in 3D space? If you look, you will see that for each of these carbon atom, there'll be one bond pointing away, towards me. There'll be another bond pointing away from me. Same goes for all the carbon atoms. All the carbon atoms, you will have one bond pointing away, one bond pointing towards you. Right. So because of this, I can have even geometrical isomerism in cyclic structures. Right. For example, if I write cis 1, 2 dimethyl cyclohexane, right? Now what you have to do is you should put the two methyl groups, either both of them to be pointing away, or both of them should be pointing towards you, same side. That's what I'm telling, both pointing away or both pointing towards you. So here you have put the first methyl group to be pointing towards you. If that's the case, there is no other choice. If it is cis, you have to put the next methyl group also to be pointing towards us, right? Or if you had have put the methyl group like this, okay, doesn't matter. So if I have put the methyl group pointing away from me, you should have put the methyl group here also to be pointing away from me. So both are the same, cis, right? But in case of trans, right, you see that if you put the first methyl group to be pointing away from you, you have to put the next one to be opposite. That is, if you put the first methyl group to be pointing away, this methyl group should be pointing towards you. Cis and
I
trans.
have a doubt.
Yeah.
So, like for example, we put one methyl group towards us.
Okay.
That means wherever we put methyl group in the cyclic compound, it should be towards us.
Sorry, come again.
If we take one methyl group, sir, and
Okay.
it's pointing towards us,
Okay.
then wherever we put another methyl group in the cyclic compound, it should be towards us. Or can
Depends
it be
on whether
other
it's cis or trans, right? If it is cis, yeah, you should be treated on the same side. If it is trans, opposite side. Say, I can even have, maybe I'll give you one more example. Say I have trans 1, 4. All right, I'll not write like this. Trans cyclohexane 1, 4 diol. Can I write the structure? Just try. I'll anyways give the structure to you. Trans cyclohexane 1, 4 diol. Just go for it. Guys, everybody try, please. So it's not like 1 and 2 first and second position. You have to take the first and fourth carbon atom. Now it is trans. Hope you remember. Okay, done. Pretty simple, right? Okay, so let me draw. Okay, now this is a cyclohexane ring. Now you have two OH groups. There's a diol, right? So two OH groups are going to be there. Now they have said it is trans, right? So you can, in the first carbon atom, you can either put the OH group pointing away or pointing towards. It doesn't matter, right? Okay, so let me put it pointing towards me. OH, no issues. Now this is 1, 2, 3, and 4. This is the fourth carbon atom. Right. Okay. Now you have put the first OH pointing towards you. Right. Now there is no other choice. If it is trans, you have to put the next OH pointing away from you. That's it. Right. If it was cis, this also would have been pointing towards us. That's it. That's what is geometrical isomerism. Understood?
Understood, sir.
Yes. Guys, everybody understood? Just give me a yes.
Yes, sir.
Actually, I have a doubt, sir.
Yeah.
Now, for example, we have to put another OH group, sir. Then how would it be? So would it be in cis or trans?
Okay. Okay. So, okay, fine. That's a nice question, actually. So what happens is, people, you can talk cis, what to say, you can talk cis or trans only with respect to two of the groups, right? Say, how do I, now if I want to put the third OH group, for example, right? Now third OH group, I can say I put it anywhere. Now you have to ask the question. You have to ask the question to me, or I have to ask the question to you, with respect to which OH group. For example, again, you can ask me whether it's cis or trans. Okay, I say trans, but again, that information is not sufficient, right? So why is it not sufficient? Is because the next question you should ask is trans with respect to what? With respect to which OH group? Right? Say, if I say in the second position I have a OH group, or say in this I have a OH group, right? Now you should ask me, say if I say it's trans, right? Now trans to which OH group? Whether to this OH group, trans to this OH group, or trans to this OH group. For example, if I say it's trans with respect to this OH group, then obviously I have to put the OH pointing away from me. But if I would have said that it is trans with respect to this OH, then you would have put it pointing towards you. Hope you understand what I said. Did you?
Yes, I understood.
And I'll repeat one more time, right? So you're asking if I put the third OH group, whether I should put it pointing away from me or whether I should put it pointing towards me, right? So now again, that question, I mean, that you have to ask the question of, okay, first your option is cis or trans, right? So for example, it is trans. Okay, now that information is not sufficient. Trans with respect to which one, right? Trans with respect to this one or trans with respect to this OH group, right? If it is trans with respect to this OH, in this case, you have put the OH group pointing towards you. So you have to put the OH group pointing away from me, because it is trans with respect to this one. If it was cis with respect to this one, for example, if it was cis with respect to this one, now again, same thing you would have said. Right, same side. In the sense, you would have put this OH group also to be pointing towards you. That's what you would have done. Okay, understood?
Understood, sir.
Right, but you don't have to worry this much, guys. This much they'll not ask you. Okay, right, fine. That is all about geometrical isomerism. Okay, so there is one more isomerism left, as I told you, that is about your CC single bond rotations. Okay, so that we will see next class. Okay, and with that, the isomerism part is completely over. So you have completed two things. One is the IUPAC naming, and the second one is your isomerisms. All things completed. And next would be your stabilities, carbocations, carbanions, acid strength, basic strength, inductive effect, hyperconjugation, resonance, mesomeric effect. All these things are left. And after that, we'll go for hydrocarbons. Okay, fine, guys. Thank you so much. If there's any doubt, you can ask me. Is there any? Okay, fine. Thank you so much, people. We'll meet again tomorrow.
Yes, sir.
Yeah.
Thank you, sir.
Thank you.